Today in class we talked about the electrons. We're going to start centering our study on not the full atom but just parts of the atom, and we're going to begin with the study of the electrons and where in the world are the electrons in an atom. We know that in the middle is the nucleus, and we know around is the electrons, but a lot of the study has gone on with the electrons because it is electrons that give things their properties. So the first part of this PowerPoint I'm going to kind of skim through. I did a little demo in class, and the first part of the PowerPoint explains the demo, but when we kick into the note sheet I'll tell you, and then I'll actually tell you what number I'm answering on the note sheet. Okay, first part is just a little review. Rutherford found the nucleus of the atom, and then we know that the electrons surround them, but knowing that most of the atom is empty space, but we really kind of need to know more about those electrons in order to understand chemical properties. And so we didn't just start with the nucleus and the proton. We went on and found more evidence of the electron, and that led us to Bohr. The Bohr model of the atom basically said the nucleus was in the middle, the electrons were in set energy levels going around. And what Bohr actually discovered through lots of study with gases, kind of like what I did in class, that they can actually leave one energy level and be excited to another energy level. They can actually jump levels. And his analogy would be that electrons are on like rungs of a ladder. And just as you can jump from one rung to the other, electrons can jump from one level to the other, but you can't go in this empty area here because that would be the empty space. So, and again, we'll talk more about this when we do the flame test. We'll kind of go back over what's happening. So this first part is kind of just a precursor to what's going to come later. So we kind of looked through a spectroscope. We saw that white light, when you look into a white light, it will separate into the colors of the rainbow, which is Roy G. Biv: red, orange, yellow, green, blue, and violet. Indigo you can include or not include. They have actually stopped including indigo in the spectrum. But we actually looked at some gases that weren't white, and so we saw something a little different. And what we noticed that these gases have a set pattern to them, and they all have like their own unique pattern, which makes them have their own unique fingerprint. And so we looked through a spectroscope and we saw some different gases. So this is how we know what's in stars. If you've ever wondered how we know what's on Jupiter, or how we know what's on the sun, how do we know these gases exist? It's because we looked at them through a spectroscope, and we've been able to map them out with their spectrums, kind of like DNA fingerprinting for you. This would be atom fingerprinting. So they have their own unique lines there. This is just some examples. This would be like hydrogen, and we look them under the spectroscope. We can actually determine which element we're looking at by looking at its atomic emission spectrum. It says unique to each element, just like fingerprints are to you. And it's very useful in identifying the elements. And then we did a little bit of just looking at a hydrogen. Hydrogen only has one electron. When it gets excited, this would be called ground state. You can send electricity or something through hydrogen gas, and you can make it get excited. What happens when it gets excited? It moves to different levels, such as may move to the second or the fourth or the fifth energy level. So they get excited, but after they get excited, they're going to fall back down into what they call their ground state. So the coming back down here releases something called a photon, and this is when you visibly can see it because it releases light. So a photon, which is your number 1 on your worksheet, is what is a photon, and it is just a bundle of light energy. And we can see that because it's releasing at certain wavelengths. And the reason we get the different band patterns is because some of them are coming down from the fourth, some are coming down from the second. They're coming down from different energy levels, so we see those and interpret those with different colors. So it was actually the study of light. Number 2 says, what did scientists study to lead to the current model? And they studied light. big definition there. They studied light. And so all this unit is about light in the beginning before we go further into electrons. In the state of Texas for the EOC says I have to teach you a little bit about light. The current model we'll be looking at next week is called the quantum mechanical model, and that is your answer for number 2, the quantum mechanical model. Number 3 says, what is light? Light is a form of electromagnetic radiation. So it's a wave of something. And there is a big debate whether or not it's matter or not matter. Most think it is just a wave and not considered matter. Some examples, which is your question number 5. Four good examples. Gamma rays, X-rays, radio waves, microwaves. Those are all examples of electromagnetic waves. And the thing about electromagnetic waves, all of them have the same speed. They travel at the speed of, what we call the speed of light, and that is going to be a set value that we'll be looking at in a moment, but you may have heard of the speed of light before. So gamma rays, X-rays, radio waves all go at the same speed. One of the things you'll have to do on your quiz is to be able to label the parts of a wave, and so you'll want to, on number 6, draw and label the parts of the wave. When you go from the top of one wave to the top of the other, or if you go from the bottom of one wave over here to the bottom of the other, which is off the screen, that is known as the wavelength. So it's the distance of one wave. This little imaginary line that's cutting in between the wave here, from this imaginary halfway line up to the top here, or from this line to this bottom, is called the amplitude. And for light, when you talk about higher amplitude, you're talking about brighter light. For amplitude, and when you're talking about sound waves, it will relate to loudness. How loud is it? The bigger the amplitude, the louder it is when you're talking about sound. But ours is all about light. We'll let you talk about sound and physics. Okay, this little line going through here is known as the origin. The very top of the wave is known as the crest, and the very bottom of the wave is known as the trough. So you'll need to be able to label these for your quiz, and you can pause this at any time, and this PowerPoint is also uploaded. Definition of wavelength is just the distance between two adjacent waves, which is part of the answer for number 7. It says, how is it measured? It is measured from crest to crest or from trough to trough. So that's how we measure wavelength. Number 8, the unit for wavelength is the meter. Again, you can pause at any time. Frequency, we're going to be looking at it in an equation. Well, I would like to point out this is what you're going to see in the equation for wavelength. It's this weird looking symbol that's called a lambda. Frequency is just going to be F. And frequency is basically how frequent is the waves, and it's how many waves pass a given point in 1 second. It's measured in the units called hertz, or it's called 1 per second, and per second can be written 2 ways. You can write it seconds to the negative 1, or you can write it 1 over seconds. So, hertz, Hz, or seconds to the negative 1, or 1 over seconds. This is how you're going to write frequency. Okay. Our formula that we're going to be using is C equals frequency times wavelength. The C stands for the speed of light. It is a constant, 3 times 10 to the 8th meters per second. Your F is your frequency. It's measured in hertz. And your little lambda guy here is wavelength, and it's measured in meters. And we're going to be working with this. And this works really nicely into a triangle. When you guys go to put things in a triangle, you should always put the right side on into the triangle first. And can you see that this is written as a multiplication? So in the triangle, the only way you can write as a multiplication is to put these two on bottom, and then the C would go on top. That way you can solve for any piece of this that you want. So just like when we did the mountains over at Death Valley. So these are not hard problems. This right here is the key, is that wavelength needs to be in meters. So if it's not in meters, it's not going to need to be to change. And so if we look at our first example, it said red light has a wavelength of 700 nanometers. What's the frequency? So the formula is that frequency equals, and if you think of your little thing, And I had students last year came up with Cowboy Feeds the Lamb, if you like that one, over the wavelength. And so c is the speed of light, which will be given to you. It's given to you on the EOC, so I'm going to go ahead and give it to you. 3.8 meters per second. Here's a problem. This is not in meters. This is in nanometers. So you've got to come over here and convert it. Nanometer go down, meter to the top, meters larger, and a nano is 1 times 10 to the 9th. So I've got to convert that. So 700 divided by 1 times 10 to the 9th, you will get 7 times 10 to the negative 7th. And that will give us meters. Can you see this will cancel? And that's going to get you a per second, also known as a hertz. And the way you can remember that it's a hertz, because if the frequency is high enough, your ears are going to hurt. And so that way you can remember that frequency is measured in hertz. So when I just put these numbers in my calculator, you get, and we're going to do sig digs. Yours actually has a decimal here, so there's 3. So you're going to get, you're going to get 4.29 times 10 to the 14th power, and the unit is per second, or we simply write hertz, which is Hz. And that is the frequency there. So that's just solving for one of those variables. Very much a physics type problem. Okay, we'll go on. We are now on number 13. And so it asks, how is frequency and wavelength related? And they're what we call inversely related. Wavelength and frequency, as one goes up, the other goes down. If it has a very long wavelength, then the frequency is going to be really low. If it has a very short wavelength, then the frequency is going to be very high. So short is high and long is low. There. I'll show you a picture there. So it's number 13 says, how are they related? They're indirectly related. And what does that mean? That means if one goes up, the other goes down. Question number 14. The different frequencies, when you start talking about different frequencies in light, those are going to get you the different colors or the different types of electromagnetic waves. The whole range is called a spectrum. We're going to look at the whole range here. Let me get to the next one. Here we go. If you'll look here, these are radio waves. Notice how long these waves are. Microwaves getting a little shorter. Infrared. This right here is called the visible spectrum, and this is the region that we can see. You can see UV light, X-rays getting, and then you got gamma rays that are really, really close together. If we were talking about energy, look here. What do you think has more energy? Radio waves or gamma rays? Okay, so gamma rays have lots of energy. They have a very high frequency, okay, but their wavelength is very short, very, very short wavelength here. So question number 14 says, what are the visible light spectrums? And the visible light spectrum is Roy G. Biv, which stands for red, orange, yellow, green, blue, indigo, and violet. And you can keep indigo in there just because it makes, you've probably learned Roy G. Biv. So over here we said that we had what we call low frequency. And since it's low frequency, it's going to also be low energy. Over here we've got really high frequency, so you're going to get high energy. So frequency increases as you go this way, and wavelength actually gets longer this way. So these are opposite one another. Frequency is bigger this way, wavelength is bigger this way. But notice energy. If it is low in frequency, it's low in energy. If it's high in frequency, it's high in energy. So the question 15 says, what color has the longest wavelength from our Roy G. Biv? The longest wavelength is going to be red. Which color has the largest frequency? The largest frequency is going to be violet. Which color is going to have the most energy? That's going to be violet as well. Number 8, let me click through this real quick. Again, this is just another same picture that we had before showing the same thing. Low energy here, high energy here. It's going to have low frequency here and high frequency here. So you can see if you have low energy, you have low frequency, high. So we call this a direct proportion or directly related for one another, which is what this is. The energy of is directly proportional to the frequency. And what does that mean? If one's low, the other's low. If one's high, the other's high. And then question number 19 says for you to write the formula for energy. Last year I only gave them the one, but I'm going to go ahead and give you the two of them. Last year I would make them use this one and the other one together, but I'm going to go ahead and give you this one because the EOC also gives you this one. So these are both equations. You don't have to memorize them. I'm going to give them on your formula sheet to you. And this is how we calculate energy. The big capital E stands for energy. It's going to be measured in a unit called joules. The little h stands for Planck's constant, after a gentleman that did lots of research with this energy and the spectrum, etc. And so this is a constant which will also be given to you. The unit for that is joules times seconds. And then the F in this first formula again is frequency. I didn't put the C. The C stands for the speed of light. So here's our two more equations. This one goes nice into a triangle. This one does not go into a triangle. So you can't use that one in a triangle because it's not 3 variable, it's 4 variables. But if we were to put this one into a triangle, again, you put your right side in first, and your right side has an H and an F, and so your E would go up there. Simple as that. This one, again, because it's got 4 variables do not go nicely into a triangle, so we can't put that one in a triangle. We'll actually have to use algebra to find that one. Oh, this is not correct. I had changed this PowerPoint, and then my computer got turned off, and this should be HC, and this should be lambda. This is not correct. It did not say the changes there, so that should be HC and lambda there. On your back of your periodic table that I gave you from the star chart, all 3 of the formulas are given, and this one is given to you. This is correct. What I had there was not correct. I apologize for that. So E equals HF and E equals HC divided by lambda, which is the wavelength, and then I can manipulate these formulas to solve for whichever variable. Alright, we're going to do one problem with that, and then that was the lesson, pretty much just using these equations. This is just more illustrating, showing that if you have a really long wavelength, then you've got low frequency, you've got low energy. It's kind of like a slinky. If you just barely pick it up and move it down, these are going to be nice and big and slow. But if you shake them really fast, they're going to have lots of energy. The little lines are going to be closer together, and the wavelength is going to be shorter there. So this is probably a good little overview picture there. So here's our last example. It says, how much energy does a photon have with a wavelength of 4.20 times 10 to the negative 5th meters? And I actually put an extra 0 on you guys for it to have 3 significant digits. So you've got to decide which of those. We know we want energy, so we've got to decide which formula. Since I gave you wavelength, you would want the one that has wavelength in it, since I corrected it. So you would actually want this one. That would be the... And wavelength is in meters, which is the unit I wanted. H is a constant that would be given to you. C is a constant that would be given to you. So you're just going to be plugging numbers in. H stands for Planck's constant, which, let's see, 6.63 times 10 to the negative 34th. You can see I don't even have it memorized. 6.63 times 10 to the negative 34th. And the unit for that guy was a joules times seconds. C stands for the speed of light. You've heard of E equals mc squared, right? The C is the speed of light, which is 3 times 10 to the 8th meters per second. And then you'll be dividing that by the wavelength, and you're going to always make sure that's in meters, and it is. If it's not, you do have to change it. And simply you're just putting that in the calculator. So you've got 6.63 times times 3 times 10 to the 8th divided by 4.2 to the negative 5th. So you're just pretty much plugging and chugging. You have a 0 there, so you've got 3 significant digits, 4.74 times 10 to the negative 21st. And here's our unit. It is energy. Can you see the meters cancel and the seconds cancel? And you're left with J. J is the unit we use. That is negative 21st there for energy. And so that's not a huge amount of energy, but you've got a small photon moving, so it's not giving much energy there. Alright, then you have the worksheet. The worksheet just has some problems for you to practice using the equations. So that is all the lesson. So good luck, and if you need me, come in the morning. I'll see you.